Welcome back, everybody. This is our video solution to problem 3 from Quiz 6, Fall 2023, Math 307, Linear Algebra at Cal State Fullerton. In this problem, we are given a vector space V along with subspaces U and W, such that V forms the direct sum, or is formed by the direct sum of U and W. So we recall this means V is the sum of U and W. So everything in V can be written as something in U plus something in W. But the directness of it means that this can be done in a unique way. So once I give you a little v in V, there's a unique U and a unique W in W, such that V equals little u plus little w. All right, we also are going to define a map. So this is what we have here, pi sub u. And this is going to be the projection map onto u. So we have pi sub u is a map from V to V. But actually, even though the codomain could be V here, the range is actually going to be the elements of U. So we could have written it as V to U. And the way you do it is if I have some little v in V, then I know that I can write it uniquely as a little u plus a little w, where little u is in U and little w is in W. And this sum is going to get mapped just to the little u. You just ignore the w component. All right, so this is well known to be a linear map, and our goal in this problem is to find all of the eigenvalues and eigenvectors of this linear map pi u. Okay, well, let's see how we can do this. So if we are going to have an eigenvector and eigenvalue pair, so let's let, say, some v be in V such that pi u applied to V is equal to lambda V. All right, and here, of course, V is going to be some non-zero vector because, well, if you're looking for an eigenvector, we're not allowed to take one which is 0. So assume we have that. Fine. Well, we know that pi u of V is defined, here's the projection, so let's also assume u as in U and W is in W, such that V is equal to U plus W. So we also have that pi U applied to little v is going to equal this little u. All right, this is going to equal lambda V. All right, so the U that we get is actually a multiple of the V, and that's maybe a little bit strange. Because this lambda V, right, that's just a multiple of V, and this U is actually in U, so I don't know, it just feels a little peculiar to me. But it makes me think I should try some sort of degenerate cases. So, for example, let's look at a case. What if lambda was equal to 0? Now, you might be thinking, wait, hold on, I thought you were not allowed to use 0 when we're talking about eigenvectors and eigenvalues. And this is where it's very important to remember the eigenvectors are never going to be 0, but eigenvalues are allowed to be 0. Okay, so let's see if we can get lambda equals 0 as a possible eigenvalue. So if this was true, if lambda is equal to 0, then we'd have u is equal to, well, it was lambda v, but lambda is now 0v, which is equal to 0. So u would equal 0, which means that v, remember, this was u plus w. This would now be 0 plus w, which is just w. Okay, of course, little w here is an element of w. And that would mean that your v has to be some non-zero element of w. Okay. So if I take some non-zero element of w, right, so if little w is an element of w but non-zero, then pi u applied to w is going to equal 0, right? Because there is no u component to it. You just have the w component to it, right? That's where the uniqueness, right, of this representation is very important. Okay, and of course this is equal to 0 times w. So in fact, lambda equals 0 is going to be an eigenvalue, provided that w is not the 0 vector space. So assuming w itself is not the 0 vector space, right? We have lambda equals 0 is an eigenvalue, And what are the corresponding eigenvectors? It's going to be all of the non-zero elements of W. So with eigenvectors, everything non-zero, right? Or if we wrote it in our alternative language here, E not equal to 0 of pi u comma 0. So this is going to be the non-zero eigenvectors for the linear map pi u corresponding to the eigenvalue 0. This will equal the non-zero elements of W. Okay, so that handles the 0 case. So what if lambda is not 0? So if lambda is not 0, well, I still have that lambda v is equal to u, but because lambda is non-zero, it has a multiplicative inverse. Remember, lambda is some complex number. So if it's non-zero, right, it's invertible. So that would tell you that v itself is equal to lambda inverse times u. But if I multiply an element of u by a constant, I still have an element of u. And that tells me that my original v is already in u. So my actual decomposition, right, it was v equals u plus w, but if v is in u, then you can't have a w. This has to be u plus 0. So in fact, my v is just equal to u. So u is equal to v, but v is equal to lambda inverse times u. Well, that doesn't seem like that's going to happen too often. Your intuition is probably that this lambda inverse is equal to 1, and you'd be right, but let's verify it. So I can subtract a u, and I get lambda inverse u minus u is equal to 0. And now I can factor out a u. And I get lambda inverse minus 1 by u is equal to 0. All right, but we had a homework problem early this semester. It said if we're working in a vector space and we multiply a scalar by a vector and I get 0, then either the scalar is 0 or the vector is 0, or of course it could be both. Now, we don't want our u to be 0 because that would mean v is 0, right? And we made an assumption up above that v was non-zero. So we know here that the u is not equal to 0, and therefore we conclude that lambda inverse minus 1 has to equal 0. Of course, this is equivalent to saying lambda inverse is 1, but of course the multiplicative inverse of 1 is 1 itself. All right, so in fact we're only going to be getting 2 eigenvalues. We had the 0 from up above, and now we get 1 as an eigenvalue. All right, so therefore, again, assuming u itself is not 0, so assuming u is not the 0 space, we have lambda equals 1 is an eigenvalue of pi u. And what are the eigenvectors? Well, the eigenvectors are just going to be all the elements of u that are not equal to 0. So with eigenvectors, u not equal to 0. So the non-zero elements in the eigenspace corresponding to 1 are precisely the non-zero elements of u. Okay, so there we go. We have found our eigenvalues 0 and 1. We have found our corresponding eigenvectors. Now, I did make these little extra assumptions here, right? That u and w were not 0. So what would happen if one of those was equal to 0? So if w is equal to 0, well then pi u, what does this do? Pi u takes an element in u and returns it to u, and it does nothing. It just takes that u part, which is itself. So this would equal the identity map, right, on v, because v is now equal to u, right? So v is equal to u in this case. And in this case, we know that every element is an eigenvector, except for 0, of course, and the eigenvalue is just 1. So in this case, the set of eigenvalues, remember that's sigma of, in this case, pi u, is just equal to 1. And then the corresponding eigenspace without 0 would just be everything. All right, so this is just going to be v not equal to 0. And what if u was equal to 0? So if u is equal to 0, well then all we have is the w, which means when you project onto u, you get nothing, right? So then pi u, well, what does it do? It's trying to send it to the u component, of which it's just 0. So this is the 0 map. All right, so this is the 0 map. I'll write it like 0 map here, which means that everything is getting mapped to 0. So in this case, the set of eigenvalues is just going to be the 0, 1. And the eigenvectors are just going to, again, be everything which is not equal to 0. All right, they all get mapped to 0. So there we go. All right, so those are the two degenerate cases. All right, I hope this is helpful, and we will see you next time.